Okay, so here's an additional example of an electron moving within a uniform electric field between two parallel plates. So the electron enters at point A and has a velocity of 2 times 10 to the 7 meters per second. At point B, it enters the uniform electric field between these two parallel plates, which have a potential difference of 200 volts across them and are 12 centimeters apart and 20 centimeters long. And it follows the curved path between B and C and has displacement S at point C, and then follows this straight path from C to D. And we've got a number of questions to look at. Calculate the electric field strength between the plates, calculate the gravitational force, calculate the force due to the electric field, calculate the acceleration of the electron upwards, and calculate the time for it to pass through the plates, and ultimately the displacement of the electron S. And we're then asked to explain the path A, B, C, D that the electron has followed. Okay, so we'll start with the first question there. Calculate the electric field strength between the parallel plates. So here the electric field is uniform, and the relationship for the electric field strength between uniform plates is that the electric field is the potential divided by the separation between the plates. So here we have a potential of 200, and we have a separation between the plates of 12 centimeters or 0.12 meters, which gives us an electric field strength of 1700 newtons per coulomb, or if we wanted, we could put the unit as volts per meter. Both are acceptable for that. Okay, we're then asked to work out the gravitational force acting upon the electron. And the gravitational force is the same as the weight, and the weight is m times g, with the mass of the electron from the datasheet being 9.11 times 10 to the minus 31 multiplied by the gravitational field strength to give us 8.93 times 10 to the minus 30 newtons. Part C asks us to work out the force due to the electric field on the electron. Okay, so the force due to the electric field, F, is equal to QE, where Q is the charge on an electron, 1.6 times 10 to the minus 19 from your relationship sheet, multiplied by the electric field strength that you calculated earlier, and this gives you 2.72 times 10 to the minus 16 newtons. So within those two parallel plates, the electron has the force downwards of the weight and the force upwards due to the electric field, and we can see that this force 10 to the minus 16 is significantly greater than the weight, so the weight is effectively negligible. The unbalanced force will be the force due to the electric field. Okay, so D asks us to work out the acceleration, so we're going to use Newton's second law here. F equals ma, looking at our unbalanced force. In this case, the unbalanced force, as we have stated, is those two take away each other. This one's so tiny, this will be the unbalanced force. So 2.72 times 10 to the minus 16 will be our unbalanced force multiplied by the mass of the electron, 9.11 times 10 to the minus 31, times the acceleration. So the acceleration ends up being 2.99 times 10 to the 14 meters per second squared. Okay, so we're now asked to work out the time that it's going to take to pass through these parallel plates, and this is going to use the information that we're given right at the top of the question. If we go back to that, there we had its constant velocity of 2 times 10 to the 7 meters per second horizontally as it entered our system at A. Because horizontally there are no forces acting, time is distance over speed, or if you prefer, displacement over velocity. doesn't matter, they're both the same in this case, and the length of the plates that it's going to travel through, also given at the top here, is that they are 20 centimeters long. And so we've got 20 centimeters divided by the speed that it is traveling at, which is 2 times 10 to the 7 meters per second. And that gives us a time of, let's just work this one out, just to check I've got it right. 1 times 10 to the minus 8 seconds for it to pass through those particular plates. So whilst it's passing through the plates, it's experiencing a constant force upwards because there's a constant acceleration, because there's a constant electric field. And question F asked us to work out the displacement of this electron. So to do F, what we have to do, let's just move it up here, so we're working out displacement here, is like our equations of motion, we write out our quantities. And we write in what we know about them already. So S is what we want to work out, it's displacement. U is its initial velocity, but it's an initial velocity vertically. So that will be 0 meters per second. We don't know how fast it's going vertically afterwards. We do know that it's accelerating at 2.99 times 10 to the 14 meters per second squared. And we've just worked out that the time is 1 times 10 to the minus 8 seconds for it to pass through those parallel plates that are 20 centimeters long. So looking at equations of motion, we can see that we can work out the displacement from S equals ut plus half at squared. So u is our initial velocity, t is our time, a is our acceleration due to the unbalanced force acting upwards due to the electric field, and we substitute in all of those, and we end up with an answer for our displacement. So first term is obviously 0, 0 times u times t is 0. So we've got 1 times 10 to the minus 8 squared times 2.99 10 to the 14 times a half. So that gives us a total of 0.015 meters, or 1.5 centimeters. As its deflection. Okay, so the plates are 12 centimeters wide, and it's moved 1.5 centimeters upwards. Okay, and the final part of the question that we're asked to explain the shape of the path A, B, C, D that the electron follows. Okay, and that's here. So between A and B, there are no forces acting on the electron because the gravitational force is almost negligible. Between B and C, there is the force due to the electric field, but we can be more precise about that because we've got a constant electric field. There is a constant acceleration upwards, or a constant force upwards, and so it follows a curved path. Because there are no forces acting horizontally, the horizontal velocity stays the same. So there's a constant acceleration upwards due to the uniform electric field, and there's a constant horizontal velocity, which is how we would describe a projectile. When it reaches C, there's no longer any electric field acting upon it, so there's no forces acting upon it because the weight is negligible, so it follows a straight path to point D.